We share this planet with a staggering variety of life. To put the sheer volume in perspective, scientists have recorded more than 20,000 distinct species of ants. If you count beetles, that number jumps to 300,000. To describe this overwhelming scale, the sociobiologist Edward Wilson popularized the term biodiversity. Biodiversity functions across three distinct tiers. There is the genetic variation within a single species, the species diversity within a specific region, and ecological diversity, the broad variety of entire ecosystems like deserts, rainforests, and coral reefs. Right now, researchers have officially described and named about 1.5 million species, but statistically, that is only a fraction of what is actually out there. Conservative estimates place the global number of species at roughly 7 million. That means humanity is living inside a vast, ancient library, but we have only managed to read roughly 22% of the titles on the shelves. Figuring out what remains on those unread shelves is difficult because our records are heavily skewed. For many groups of plants and animals, our species inventories are much more complete in temperate countries than they are in the tropics. Because an overwhelmingly large proportion of undiscovered species live in those tropical zones, biologists rely on a specific mathematical method. They take an exhaustively studied group of insects, compare the ratio of temperate to tropical species, and apply that ratio across other taxonomic groups to estimate the global total. When you apply this math to a specific region, the results are incredible. Take India. It covers only 2.4% of the world's land area, yet it holds an impressive 8.1% of the global species diversity. Based on those extrapolation models, researchers estimate there are still over 100,000 plant species and more than 300,000 animal species in India waiting to be discovered. Completing this inventory requires a massive commitment of time and trained taxonomists. Given the scale of the undiscovered life in India alone, cataloging this biological wealth represents one of the most significant scientific challenges of our time. Long before we had global statistical models, early scientists tried to find a natural order to this diversity. During his extensive explorations of the South American jungles, the German naturalist Alexander von Humboldt started mapping exactly how life is distributed. He observed a pattern we now call the latitudinal gradient. Simply put, species diversity drastically increases as you move away from the poles and travel toward the equator. The regional counts prove the rule. Greenland, located up at 71 degrees north, has only 56 species of birds, but Colombia, sitting right near the equator, harbors nearly 1,400. Biologists point to three reasons for this tropical abundance. First, unlike temperate regions, the tropics remained relatively undisturbed by frequent Ice Age glaciations, giving species millions of uninterrupted years to evolve. Second, tropical environments are less seasonal and more constant, which promotes highly specialized niches. And third, these regions receive significantly more solar energy, directly fueling higher plant productivity. As a result, the bulk of Earth's biological library is heavily concentrated in these equatorial zones, making them critical ecological vaults. Humboldt noticed another hard rule in these jungles regarding species-area relationships. As you explore a larger area of land, you will find more species, but only up to a very specific mathematical limit. This diagram shows that relationship. When you plot species richness against the explored area for a wide variety of taxa, the result is a curve called a rectangular hyperbola. When we convert this chart to a logarithmic scale using the standard equation, the curve becomes a straight line. What is truly strange is the slope of this line, represented by the letter Z. Whether you are counting plants in Britain, birds in California, or mollusks in New York, that slope consistently falls between 0.1 and 0.2. However, if you expand your measurement to encompass entire continents, that slope suddenly gets much steeper, shifting into the range of 0.6 to 1.2. This math tells us how life fills a physical space, but it also warns us about stability. Stanford ecologist Paul Ehrlich compared this dynamic to an airplane in his rivet popper hypothesis. Every species is a rivet holding the ecosystem together. Popping one or two out might not cause an immediate crash, but as you remove more and more of them, the structural integrity of the entire machine becomes dangerously weak. Earth has experienced 5 mass extinction episodes in its 3 billion-year history. We are currently in the middle of a 6th extinction, but this time, human activity is the sole driver. The defining feature of this crisis is its velocity. The current rate of species extinction is estimated to be 100 to 1,000 times faster than in pre-human times. These losses are not random across the tree of life. Groups like amphibians are uniquely vulnerable to rapid environmental shifts. Today, over 15,500 species worldwide are actively facing the threat of extinction. We have undeniable photographic and historical proof of what this looks like. Over the last few centuries, we have completely erased unique animals like the dodo and the thylacine from existence. Humanity spent the last few centuries mapping the mechanics of our biosphere, and now we are actively dismantling the very planetary machine we set out to understand. Biologists point to 4 major causes driving this collapse, often called the evil quartet. The most destructive driver by far is habitat loss and fragmentation. Historically, tropical rainforests covered more than 14% of the Earth's land surface. Today, they cover no more than 6%. The sheer scale of this destruction is visible from the sky. In the Amazon, vast swaths of complex jungle are actively burned and cleared out, replaced by soybean farms and grazing land for cattle. When you remove a habitat like this, you trigger immediate biological consequences. Total plant production drops, the environment loses drought resistance, and disease cycles become highly volatile. It took millions of years of evolution to accumulate this rich biodiversity, yet we could lose all of that wealth in less than 2 centuries. We are setting fire to nature's biological library before we have even cataloged the books inside, risking the collapse of the planet's life.